Now we calculating the Euler head for the Pelton wheel. So this is the velocity triangle for Pelton wheel. And in previous lesson, we know that Euler head can be written as 1 over g u1 v1 minus u2 v2. And because in Pelton wheel, we assume that tangential velocity u1 is equal to u2, so we could write the tangential velocity as u. Then we could simplify the equation for Euler head becomes u over g v1 minus v2. Then we substitute the value of v1 and v2 that we get from the previous calculation. v1 is assumed to be equal to v1, and v2 is calculated, and we have it is equal to u minus k vr1 cos 180 minus theta. Then we substitute the value of vr1. As you could see here, vr1 can be written as v1 minus u. So we substitute the value of v1 minus u here. Then we could get this equation. We could simplify this term into this one, u over g v1 minus u 1 minus 1 plus k cos 180 minus theta. In some textbook, they will write 180 minus theta means the angle of this area is equal to beta 2. It is equal at this angle also. So, as in some textbook, they will write Euler head is equal to u over g v1 minus u k 1 plus k cos beta 2. And this is the power of Pelton wheel. We know that the power can be calculated by using rho GQH, and to calculate the power from Pelton wheel, we will use Euler head as our turbine head here. So we substitute the value of HE. Here we could get rho GQ u over g v1 minus u 1 plus k cos beta 2. And then we could cancel the value of gravity here, so it's become rho q u v1 minus u 1 plus k cos beta 2. I hope you could remember this equation. So this is the another example of velocity triangle that draw like this. So this is the imagination of bucket from the top view. So you may draw like this. So you have a V1 here, and then you have the U here, and this textbook is Potter textbook. So it write VR1 is equal to small v1, and the absolute velocity is capital V1. So this is just the term of how to write the symbol here. So we have a V2 here, and also we have VR2 here, and this is the tangential velocity U. So this means that if you see this velocity triangle, so this means that it draw the velocity triangle from the top view like this. And previously I show you the velocity triangle that draw in side view. So now we are discussing about the efficiency of Pelton wheel, because we already know how to calculate the power. The first one is the hydraulic efficiency. We could write as eta hydraulic is equal to power out divided by power in, and it can be write as rho GQ Euler head as the output and rho GQ effective head as the inlet here. So the Euler head here can be substituted with this term 1 over g u v1 minus u 1 plus k cos 180 minus theta. And H effective here can be substitute with this equation, v1 square over 2g. This is the way we calculate the velocity head. So, and then we could simplify this term by cancelling the value of g here. We could get that it is equal to 2u v1 minus u 1 plus k cos 180 minus theta over v1 square. To get the maximum efficiency, we differentiate the term and equate it to 0. So we differentiate d eta hydraulic over du and equal to 0. So we get the value of, we substitute the value of eta hydraulic here. So we substitute, we differentiate it to du. We could get 2v1 minus 4u times 1 plus k cos 180 minus theta over v1 square. The second terms here cannot equal to 0. So the only possibility to equal to 0 is 2v1 minus 4u. So we calculate 2v1 minus 4u equal to 0. We could get u equal v1 over 2. It means that to get maximum efficiency in Pelton wheel, the speed of wheel u must be half of the velocity of water jet, which is v1. And this is the graph of hydraulic efficiency and the speed ratio phi. So we found that in theoretical, the curve will become like this. So, but the experimental or the actual will show in dotted line like this. It is happen because in actual we have friction, resistance, and everything need to be accounted. So why we differentiate d eta over du equal to 0? Because we want to take the maximum point here to calculate the maximum efficiency. So it is found that the maximum efficiency is actually occur when the value of phi here is equal to 0.5. So in next lesson, we will say that the ratio of u over v1, if we take this v1 to the left side here, u over v1 is equal to 1 over 2. So 1 over 2 is equal to 0.5. So u over v1 or u over vj can also be assumed is equal to speed ratio of phi here. Then we know that the hydraulic efficiency can be written in this term. We substitute the value of u equal v1 over 2. We could get the hydraulic efficiency is equal to 1 plus k cos 180 minus theta over v1 square. And this is the hydraulic efficiency at maximum condition. Then from previous lesson, we know that the power can be written as P equal rho QU V1 minus U 1 plus K cos 180 minus theta. We substitute the value U equal V1 over 2. We could get power is equal to rho Q V1 square over 4 1 plus K cos 180 minus theta. So this equation is the power at the maximum condition. Next, we will discuss about the mechanical efficiency. The idea is power out divided by power in. So the mechanical efficiency can be written as power at turbine shaft as the power out, and power produced by the wheel is the power inlet. So we could replace the power produced by the wheel by this equation mean rho GQH Euler heat. So it can be written as rho QU V1 minus U 1 plus K cos 180 minus theta here. And P out here is actually power that comes out from the turbine. Normally in our syllabus, the power out here will be given in the question. So this is the overall efficiency. We could write as eta O here, and it is equal to power at turbine shaft divided by power from the water jet. Please be remember that the water jet here is the first energy head that comes into the turbine system. So it will become the inlet here, and turbine shaft is the last point where the power comes out from the Pelton wheel, so it will become the power out. So again, the power at turbine shaft or power out here will be given in the question. And to calculate the power from the jet, we will use the equation of rho GQ times effective heat as the power input here.